हेलो स्टूडेंट्स, वेलकम टू माय यूट्यूब चैनल जिसका नाम है आओ केमिस्ट्री सीखें। लेट्स एंजॉय केमिस्ट्री। अपने इस चैनल पर आज मैं आपके लिए इलेक्ट्रोकेमिस्ट्री का एक इम्पॉर्टेंट टॉपिक लेकर आया हूँ जिसका नाम है डिबाई-हकल-ऑनसेगर समीकरण। इट इज़ द डेरिवेशन ऑफ Debye-Huckel-Onsager equation. This particular equation is one of the most important concepts of electrochemistry of strong electrolytes. ये particular concept MSc के स्टूडेंट्स के साथ साथ नेट की प्रिपरेशन करने वाले स्टूडेंट्स के लिए भी काफ़ी उपयोगी है। सो आओ केमिस्ट्री सीखें। लेट्स एंजॉय केमिस्ट्री। डियर स्टूडेंट्स, before moving to the derivation of Debye-Huckel-Onsager equation, let's have some background of this equation. Actually, what happened in the early 20th century, researchers were trying to account for the falling off of the equivalent conductance of strong electrolytes at appreciable concentrations. That means, जब किसी strong electrolytes जैसे NaCl का सॉल्यूशन बनाया जाता और उसकी इक्विवेलेंट कंडक्टेंस मेजर की जाती तो उसकी कुछ वैल्यू आती, और जैसे जैसे सॉल्यूशन का कॉन्सेंट्रेशन बढ़ाया जाता सॉल्यूशन के इक्विवेलेंट कंडक्टेंस में कमी देखी जाती। और रिसर्चर्स ये पता करने की कोशिश कर रहे थे कि व्हाट वाज द रीजन बिहाइंड द फॉलिंग ऑफ द इक्विवेलेंट कंडक्टेंस एट एप्रिशिएबल कॉन्सेंट्रेशंस। तमाम रिसर्चर्स की इसी कोशिश के बीच रशियन वैज्ञानिक कोहलरॉस ने एक्सपेरिमेंट्स के आधार पर एक नियम दिया जिसमें उन्होंने कहा कि डिक्रीज इन द इक्विवेलेंट कंडक्टेंस इज प्रोपोर्शनल टू द स्क्वायर रूट ऑफ द कॉन्सेंट्रेशन। दैट इज, इक्विवेलेंट कंडक्टेंस में जो कमी है वो कॉन्सेंट्रेशन के स्क्वायर रूट के प्रोपोर्शनल होती है। ये एक एम्पिरिकल रूल था और इस रूल को सपोर्ट करने के लिए डिबाई और हकल ने भी कोशिश की। एंड अकॉर्डिंग टू डिबाई एंड हकल, दे ट्राइड टू एक्सप्लेन इट इन टर्म्स ऑफ डिक्रीज इन आयनिक वेलोसिटी रिजल्टिंग फ्रॉम इंटर आयनिक फोर्सेस। इस पर्टिकुलर कॉन्सेप्ट को हम लोग डिबाई-हकल थ्योरी में काफ़ी विस्तार से पढ़ चुके हैं और इस थ्योरी का जो वीडियो मैंने यूट्यूब पर अपलोड किया है उसका लिंक डिस्क्रिप्शन में दिया गया है। इन दिस पर्टिकुलर थ्योरी, डिबाई एंड हकल हेल्ड टू इफेक्ट्स रेस्पॉन्सिबल फॉर डिक्रीज इन द आयनिक वेलोसिटी। दीज टू इफेक्ट्स आर रिलैक्सेशन फोर्स एंड द सेकेंड वन इज इलेक्ट्रोफोरेटिक फोर्स। और इन दो इफ़ेक्ट्स और फोर्सेस की सहायता से उन्होंने समझाया कि किस तरह से किसी सॉल्यूशन के अंदर आयन की गति, आयन की वेलोसिटी कम हो जाती है और वह अपने इलेक्ट्रोड की ओर अपेक्षाकृत कम गति से चलता है। लेकिन थिंग्स वर नॉट सॉल्व्ड, क्योंकि उसी समय एक और यंग रिसर्चर लार्स ऑनसेगर was not satisfied with Debye-Huckel limiting law or even Debye-Huckel theory. लार्स ऑनसेगर ने डिबाई-हकल थ्योरी को इम्प्रूव किया। ये भी हम लोग अपने पिछले लेक्चर्स में पढ़ चुके हैं। हाउ डिड ही इम्प्रूव डिबाई-हकल थ्योरी? लेट्स हैव ए जिस्ट। As Onsager was not satisfied with Debye-Huckel theory, in his bit he tried to improve it. He added Brownian movement of ions which result due to collisions of ions with the surrounding solvent molecules. Also, Onsager derived an expression for electrophoretic force which act on the ith kind of ion. And while deriving this expression, he didn't use Stokes' law for the ion. Here is the expression of electrophoretic force derived by Onsager. Also, Onsager derived an improved expression for relaxation force, taking Brownian moment of the ions into account. Here is the expression derived by Lars Onsager. Also, he considered the effect of frictional force of the solvent on the ionic moment. Here is the expression of frictional force. It is a general expression. So, according to Onsager's modification, there are three forces acting on a moving ion. These are namely electrophoretic force, relaxation force, and frictional force of the solvent. These three act on the ion and oppose its movement. Here are the expressions for these three forces, and moving to next slide. Various symbols used in these expressions have their meaning, like Ki is the frictional coefficient on ith ion due to solvent, Ui is the ionic mobility. That means it is the steady velocity of the ith ion. E is the electronic charge, Zi is the valency of ith ion, kappa is the reciprocal of thickness of ionic atmosphere. If you remember, we had derived its expression, and today we are going to use this expression later on. Capital V used is the potential gradient under which ith ion is moving. It is defined as the difference of the potential per unit length. Eta, as usual, is the coefficient of viscosity, and W is a number which is defined mathematically as W is equal to Z plus into Z minus into 2Q upon 1 plus root Q. Here Q is another number. It is given by this lengthy expression. For an electrolyte like NaCl, value of W and Q has been calculated here for your ready reference. For NaCl, valency of cation, that is Z plus, is equal to 1, and valency of anion, that is Z minus, is also 1. Chloride ion's valency is 1 and sodium ion's valency is also 1. So, by formula of Q, Z plus and Z minus can be substituted here. On substitution, we get an expression like this. Here lambda plus and lambda minus can be cancelled out. So, value of Q comes as 1 by 2. So, value of W can be calculated from this expression by substituting value of Q, and it comes out like 2 minus root 2. So, for 1:1 electrolyte like NaCl, value of W is 2 minus root 2. These are some numbers used in the expressions of electrophoretic force, relaxation force, and frictional force of the solvent. So, students, we are about to start the derivation of Debye-Huckel-Onsager equation. But prior to it, let us understand what is the actual picture in the solution of strong electrolyte. Here is the visualization. You can see these are two electrodes, cathode and anode, and here are the cations and anions present in the solution. When the external electrical field is applied, these ions move towards their respective electrodes, and their motion, you can see once again, they move towards their electrode in a zigzag motion, that is the Brownian movement of ions. Once again, ions are present in the solution, and under the influence of external electrical field, they move towards their electrodes. While moving towards the electrode, ions are attracted by the electrical force, which is given by external source. At the same time, according to Onsager, there are three forces which are opposing the movement of these ions. These three forces are electrophoretic force, relaxation force, and frictional force of the solvent. So what happens when a given ion in the solution tries to move towards its electrode under the influence of external electrical field, and its motion is opposed by three forces? According to Lars Onsager, when a given ion moves towards its electrode and three forces are opposing its motion, then what happens? There comes an equilibrium between the force which is accelerating it towards the electrode and three forces which are pulling it back. So there comes an equilibrium and the moving ion acquires a steady velocity. At this steady velocity, the ion experiences zero resultant force, as the force due to external electrical field is exactly balanced by the sum of three forces acting on the opposite direction. What are these three forces? These are namely relaxation force, electrophoretic force, and the third one is frictional force of the solvent. First, what is the electrical force acting on a given ion? Electrical force by formula is given as charge of the ion into the potential difference, and in this case the charge is E into Zi, where Zi is the valency of ion and E is the electronic charge. So total charge on ith ion is Ezi into, it is accelerated by a potential difference of V. So electrical force on the moving ion is Ezi into V, and electrophoretic force is given by this expression. Relaxation force is given by E cube Zi kappa upon 24 epsilon epsilon naught kBt into W into V, and frictional force of the solvent is given by Ki into Ui. Now, according to Lars Onsager, when the moving ion acquires steady velocity, at that time electrical force is equal to sum of these three forces which are opposing the motion of the ion. So electrical force Eziv is equal to electrophoretic force plus relaxation force plus frictional force. We can rearrange this equation so that Kiui comes in the beginning and the first term, relaxation force, goes to last. So it becomes like this. Now what we do? We divide this equation by Kiv. So dividing the whole equation by Kiv, we get a simplified equation like this. It is Ezi upon Ki is equal to Ui upon V plus Ezi kappa upon 6 pi eta plus E cube Zi kappa upon 24 epsilon epsilon naught kBt into W upon Ki. We rearrange this equation in such a way that these two terms present on RHS go to LHS. So the equation takes this form. Now we take the common terms out from these two, the new equation takes a shape like this. Here E into kappa are the common terms taken out. Now what we do? We consider that the ith ion is moving under the influence of unit potential gradient. Unit potential gradient V is equal to 1, or in ESU, that is electrostatic unit, the value of V becomes 1 by 300. So substituting this value in the above equation, we get an equation like this. 1 by 300 was substituted here, and this 300 was taken from LHS to RHS. Since it was 1 by 300, on taking to RHS, it was multiplied to the denominator here as well as here. So we get an equation for UI. Let us modify it further to get the desired equation known as Debye-Huckel-Onsager equation. For a given ion, equivalent conductance lambda I is related to the ionic mobility Ui by the expression lambda I is equal to Ui into F, where F is Faraday constant. So from this expression, we can write Ui is equal to lambda I upon F. Also, let us consider the case at infinite dilution. At infinite dilution, ionic mobility Ui can be written as limiting ionic mobility, that is U naught I. Also, kappa becomes 0 at infinite dilution, because in the expression of kappa there comes a term sigma Ni Zi square, and it becomes 0 at infinite dilution. So we had obtained this equation. We can modify it at infinite dilution. We can write it as U naught I is equal to Ezi upon 300 Ki, because this kappa becomes 0 at infinite dilution. So this equation is limited to this term only. So U naught I becomes this at infinite dilution. Also, at infinite dilution, the limiting equivalent conductance of ith ion, which is written as lambda naught I, is related to its limiting ionic mobility U naught I as lambda naught I is equal to U naught I into F. It is this expression only, but applied to the infinite dilution. So this equivalent conductance becomes limiting equivalent conductance, and Ui becomes limiting ionic mobility. So expression becomes lambda naught I is equal to U naught I into F. From this we can write U naught I as lambda naught I upon F. If we equate this particular equation with this equation, we get something like this. Lambda naught I upon F from here is equal to Ezi upon 300 Ki. Now we substitute these values here. So this equation becomes a simplified equation. Ezi, this is modified, it becomes Ezi upon Ki is equal to 300 into lambda naught I upon F. Now we substitute these values in this equation. A simplified equation comes. Instead of Ui, we can write as lambda I upon F. Then instead of Ezi upon 300 Ki, we write something like this, lambda naught I upon F and Ek upon 300 is still here, and here we can change it according to this 300 into lambda naught I upon F. So we get a simplified equation in terms of equivalent conductance and limiting equivalent conductance. So dear students, we are very close to Debye-Huckel-Onsager equation. Now inside the bracket, instead of Ezi upon Ki, we substitute the value as 300 lambda naught I upon F. So on substituting this value, the equation becomes like this. Here we have substituted the value. Now what we do, we multiply the whole equation by F so that these F terms get cancelled out. On multiplying the equation by F, we get lambda I is equal to lambda naught I minus a big term. Here F comes and here F goes from the denominator. Now we substitute the value of kappa. If you remember, value of kappa is something like this. This kappa inverse is known as thickness of ionic atmosphere, and its expression is given like this. So on substituting this kappa here, we get an equation like this, where this kappa has been replaced by its expression. Now this particular expression of equivalent conductance of ith ion has some constant like E, Na, Boltzmann constant Kb, epsilon naught, epsilon, F, that is Faraday constant. So if we calculate the values by substituting these constants, we get a simplified equation where 29.15 has come in the numerator of the first term inside the bracket, and this 9.9 into 10 to the power 5 has come in the second term inside the bracket. Now we further modified it by changing something here. This Ci is the concentration of ith ion and Zi is its valency. So we change something like this. Ci is replaced with C. C is the equivalent per liter, and this C is equal to Ci into Zi. So if we substitute Ci into Zi, instead of this, if we substitute C, we get a simplified equation. In this equation, instead of Ci Zi square, we have got C into Zi, where C is the equivalent per liter or gram equivalent per liter. So this particular equation of equivalent conductance is one form of Debye-Huckel-Onsager equation, gives idea about equivalent conductance of ith ion in the electrolytic solution. We can modify this equation in various forms of Debye-Huckel-Onsager equation. In following slides, we are going to see some other forms of this particular equation. The previous form of Debye-Huckel-Onsager equation gives equivalent conductance of ith kind of ion. But for a given electrolyte, the equivalent conductance of the electrolyte is the sum of equivalent conductance of its constituent ions, that is cations and anions. So applying the previous equation to cations and anions, we get equivalent conductance of electrolyte, and the equation takes a shape like this, where a small lambda is replaced by capital lambda. Here capital lambda is the equivalent conductance of electrolytic solution. Similarly, this capital lambda naught is the equivalent conductance of electrolytic solution at infinite dilution. And instead of Zi, here we get two terms, Z plus and Z minus, which are the valency of cations and anions. Similarly, here also we get Z plus and Z minus. We can further simplify this equation by applying it to 1:1 electrolyte. That means an electrolyte which has one cation and one anion, and if valency of cation and anion is also 1, like in case of NaCl, so this equation can further be simplified. Because for such an electrolyte, the capital C, which is the gram equivalent per liter, can be substituted by molar concentration, and the equivalent conductance now becomes molar conductance for 1:1 electrolyte. For such an electrolyte, Z plus and Z minus will be 1, and we have also calculated for 1:1 electrolyte value of W will be 2 minus root 2. So on substituting these values for 1:1 electrolyte, this equation can be simplified as this. It is one of the general forms of Debye-Huckel-Onsager equation, which is applicable to 1:1 electrolyte. That means an electrolyte having univalent cation and univalent anion. Here, the first term in the square bracket takes consideration of electrophoretic force, and this second term, it takes consideration of relaxation force. If you see, here we have small c, it is the molar concentration, and it can further be simplified by writing like this: lambda is equal to lambda naught, and for first term we write A, and for second term inside the bracket, except this lambda naught, we write B. So this equation takes this form, and instead of c power root 1/2, we can write it as under root c. So this is one of the most familiar forms of Debye-Huckel-Onsager equation. Here in this equation, A is the term which depends on absolute temperature and coefficient of viscosity, whereas B is the term which depends on absolute temperature of the solution apart from dielectric constants. So one important question which may be framed from this portion of Debye-Huckel-Onsager equation is, first, what do these A and B stand for? The answer is the first term, the term which does not have lambda naught. It may be written as A or sometimes it may be written as B. So the term which doesn't have lambda naught, that stands for electrophoretic force. And the second term which is multiplied with lambda naught, that stands for relaxation force. This is one important concept. And second, on which factors do the value of A depend? The answer is value of this term depends on absolute temperature and coefficient of viscosity and dielectric constant of the solvent, whereas value of the second term, which is present along with lambda naught, depends on temperature and dielectric constant of the solvent. Its value doesn't depend on coefficient of viscosity. So these are two important questions which may be framed from Debye-Huckel-Onsager equations expression. Now coming to the last part of our derivation, that is limitation of Debye-Huckel-Onsager equation. This particular equation was a modification upon Debye-Huckel limiting law, and this equation can simply be written as lambda is equal to lambda naught minus within bracket A plus B lambda naught and outside bracket under root C, where A and B are the constants and lambda is the equivalent conductance of an electrolytic solution, lambda naught is the limiting equivalent conductance of the electrolytic solution, and C in this case is the molar concentration of the solution. So A and B are the two constants which depend on the nature of the solvent and the temperature. Out of these two, A is generally written as 82.4 upon epsilon naught epsilon T whole power 1 by 2 into eta, and B is written as 8.2 into 10 to the power upon epsilon naught epsilon T whole power 3 by 2. So here you should remember one thing. A means the term within the bracket that is not associated with lambda naught or free from lambda naught. This particular term depends on dielectric constant of the solution, temperature of the measurement, and viscosity of the solvent. And B means the term within the bracket which is associated with lambda naught. This particular term depends on dielectric constant of the medium and temperature of the measurement, but it is independent of eta, that is coefficient of viscosity. Why we should remember these two terms? Because at times this equation is given like this, and here you can see A is associated with lambda naught and B is independent of lambda naught within the bracket. So we need not cram that. A means it depends on dielectric constant, temperature, and coefficient of viscosity. What we should remember here, the term within bracket which is associated with lambda naught, it may be written as B or it may be written as A. This particular term is independent of coefficient of viscosity, whereas the other term within the bracket which doesn't have lambda naught, it may be written as A or at times it may be written as B. This particular term depends on dielectric constant, temperature, as well as coefficient of viscosity of the solution. So this is the thing we have to remember. And finally, this particular equation was found to follow by 1:1 electrolyte to the concentration of 2 into 10 to the power minus 3 equivalent per liters. So it is bit better than the other equation which was given as Debye-Huckel limiting law. It was followed only up to 1 into 10 to the power minus 3 for 1:1 electrolyte. So this is all about Debye-Huckel-Onsager equation. While going through the lecture, because it is a mathematical derivation, you must have to prepare the notes by stopping the video here and there. And even after that, if you have got some doubts, you please let me know. I will try to solve them. Stay home, stay safe. Thank you.